Hello, everyone. I'm Rihanna Begg, Editor-in-Chief of Machine Design. It is my pleasure to introduce John Fenske, Director of Marketing, and Mason Cousins, Controls Engineer at Tolomatic, a manufacturer of electric linear actuators and industrial-grade motion control solutions. So, from your perspective, where does real performance in in modern servo systems come from today? Are we looking at the control algorithms? Is it the mechanical design, or is there integration between the two?
I'd say it's an integration between the two. It's kind of in the name, in the question, servo systems. So it's an entire system that we're working with. I think when we look at automation, building machines, whatever it may be, we have to make sure that we're looking at it from an entire system point of view. It's not just the controls and the control algorithms that are running, and it's not just the mechanical aspects of it. And I think that's a part that gets missed commonly early on in the design of systems. A lot of times there's heavy focus purely on the mechanical side of things. And while that may help make sure that an actuator fits into a system and it can produce the force or do the speed that it needs to, that doesn't tell the whole story. And it may lead to problems down the road for controls engineers, electrical engineers, as they try to take some system that's already been developed and fit it into whatever it is that they're trying to do. So I think the biggest thing is making sure everyone's at the table when everyone's talking initially. Make sure everyone can kind of voice their concerns, what they're interested in, and everyone work together to help try to build an optimized system instead of just throwing it to one side of the engineering team once the other side's done with it.
Yeah, John, did you want to add to that? Perhaps talk about that precisely that perspective on looking at the design phase and understanding at the outset what the requirements are and how people are speccing these days.
Yeah. You're absolutely right. It's got to be from the first question you ask, right? Because as Mason said, if you start with the focus of, I want to understand, what force you're after, and what speed you're after, or what's your motion profile, that's not the right question to ask. Or, what are you trying to control, or what are the inputs to the control system? You've got to broadly understand what the customer is trying to accomplish in order to get to a workable solution. And I think, we see that really come to bear. What's driving our business largely is hydraulic conversion, right? Hydraulic and pneumatic conversion. There's a lot of electrification going on. And I think that really comes to bear when you have someone who is standing there with a hydraulic cylinder and wants to replace it, right? And there's this huge misconception that you can just drop in and replace it with an electric actuator, when in reality that it's really a system redesign opportunity, right? And when engineered correctly, you gain precision and energy efficiency and repeatability, but the transition requires discipline on both mechanical and the electrical side.
So let's drill a little bit deeper down into that. So when companies move from pneumatics or hydraulics to electric actuators, what are they underestimating? So can you perhaps talk to some of the realities or the misconceptions manufacturers face when they replace cylinders with servo-driven linear actuators?
Yeah, Mason, you want to take that one?
Yeah, sure. So I think one thing that we see commonly is when they're doing that conversion is, and it comes back to what we were just talking about of not having the controls and electrical team involved at the beginning. Um, they may, if this is their first jump into it and they're not familiar with servo systems or electric systems of some kind, they may not understand the complexity that's involved with getting that system set up and doing exactly what they want as they were before with pneumatic or hydraulic. And that's not to say that electric systems are overly complex by any means. It's just different. So there's different considerations that you need to take into account when you're designing a system. I think another one that comes into mind is the physical size, especially when you're looking at the hydraulic world. If you're taking a hydraulic cylinder, hydraulics are incredibly power dense. So if you're going to take a direct replacement with an electric actuator, it's probably physically going to be a bit bigger if you're looking at the same forces. So that's another thing that comes into mind. Another one is sticker shock. So the upfront cost of electric systems is likely going to cost more. And I think people need to make sure that when they're looking at moving into an electric system, are they taking the full picture into account when it comes to cost as well? It's not just the upfront; it's the maintenance cost. It's the cost of not only maintaining the equipment for the air compressors or the hydraulic motors that are running the HPUs. It's also how much electricity are those drawing at all times. So there's a lot of different things to take into consideration when you're moving from hydraulics to pneumatics over to electric. It's not just the surface level stuff that comes up.
Like I said, it's this misconception that it's really simple to replace hydraulic with electric, and you got to kind of think of it as an opportunity to optimize your system rather than just limping along and replacing, right? It's an opportunity to optimize, and I think our more progressive customers are definitely thinking that way.
Right. I wonder, Mason, if we can go to a little bit more to a more granular level and talking about closed loop force control change. And so how does it change the way actuators and systems must be designed, especially for force critical tasks like pressing, like clamping or forming? I wonder if you can take us a little bit deeper down to the component level and help me understand what some of the more modern take is on closed loop force control.
Yeah, definitely. This is something that we run into quite a bit, and we deal a lot with in opportunities that we work with. And this kind of ties back to looking at it from a system level from the beginning. So, at the onset of this, if force control is something that's very important for whatever the application may be, pressing, clamping, welding, whatever it is, has that been thought of at the very beginning when you're designing it? Or is it an afterthought that maybe we need to understand exactly what the force is when we are doing whatever the motion may be? In that case, you're trying to throw a load cell into the system where it wasn't designed originally. Will it fit? I think a lot of times, even something as simple as cable routing is a big concern because it wasn't thought of at the beginning of the design phase. So that can provide challenges. There's also environmental challenges with load cells. Is it in an environment that's going to be incredibly hot? Are thermals going to come into consideration? Does it need to be if it's going to be exposed externally, mounted to the end of the actuator, or the end of the tooling, or below the tooling? That may come into consideration. Tolomatic does have products that have load cells integrated inside of them. And so that eliminates a lot of those problems. You don't have to worry about cable routing, the environmental aspects. And part of the design includes as the actuators heat up from operating, that doesn't adversely impact the measurements that you're getting when you're measuring force. And I think also it comes down to the actuator selection when you're looking at doing closed loop force control. Some actuators are designed to operate probably better in that space than others may be. There's less compliance in the system because you think of it's a stack up of all the different parts in the system as you're pressing. So if you have compliance in any of those different aspects, that's going to be a potential error in your system. So there are actuator designs that have been thought of kind of from the beginning to be able to have load cells inside of them that are incredibly accurate. The systems are very stiff from the actuator point of view. And then it comes back to in the early stages of talking and design, are we selecting the right actuator for this system? And then what is that attached to? Is the tooling set up properly? Is there too much compliance in that? And then what does the actual end effect look like? Is that set up properly as well? I think a couple others I can think of is actually reading the load cell when you're doing that. Is your amp that's amping the signal, is that able to provide large enough bandwidth? Whatever you're feeding that signal into likely a PLC, which is doing some conversions on it and then sending the command over to a drive, is that able to read that fast enough? It depends on the application. Do we need really high speed readings of force, or is that not necessarily as big of a requirement? We maybe just want to know what the force was after we did a move.